And finally, we'll be hearing from Brian Albiston, who is the president of Revolution LENR LLC in Hood River, Oregon. Brian's an engineer who's been following LENR for many years and has recently started actively researching in the field as an amateur scientist. And his topic is going to be do-it-yourself LENR replication at home.
First of all, thank you very much for this opportunity. I'd like to thank the other presenters, Vladimir and Bob. Excellent. Gave me a lot of things to think about and fodder for the future experimenting. I'd also like to thank the Energy 2.0 Society for this opportunity. My presentation is going to be a lot less technical. It's really focused at the home and garage experimenter. And I just wanted to, first of all, go over what I'll be talking about today. First, why do this as a home experimenter? Then I'll just go over some of the lessons I've learned, some skills I've learned through doing this. And then if we have time, I'll go over some of my most recent results and future things I think that we could work on. So why do this as a home experimenter? First of all, it can be a lot of fun being a part of history. We are making history here. I think the group of people that we have working together, open source, to do this is something rare in history. I don't think it's, to my knowledge, has been seen before in a developing science like this. You can make a difference as a home experimenter. I think I would say that both Rossi and Goddess both started as amateur scientists. I don't think you have to be a professor in order to make a difference, and we all have something to add. The one thing that I've been really impressed with the LENR community is how willing they are to help everyone who wants to get involved in this, and that goes with Bob and everyone at the Martin Fleischmann Memorial Project. And really, I've been impressed with how accessible everyone is and how willing they are to help and provide advice. I don't have a lot of knowledge in physics and chemistry, but I do have engineering experience to add. But everyone has been very good at in helping me and giving me ideas with knowledge I lacked, and also to do these experiments safely. So really, I think that your personal willingness and tenacity are the most important requirements. It's not necessarily technical knowledge. You do, of course, need some technical skills, but the willingness is the most important requirement. And as a home inventor, I don't think that anyone is going to be necessarily convinced by the results, but I think once you've convinced yourself, then we can get other home experimenters to start trying to replicate your results. And as we do that and share the results, then we can get other people starting to believe those. But focus on convincing yourself. I think that's the most important key. And then share your results. I don't have money or ability to hire an R&D team to work with me, but the crowd has been an excellent R&D team in helping me out with things that I don't understand. And so use that, utilize it, and share your results with others. And then also consider the criticism you receive from others as a courtesy to help you become a better experimenter. Let's see. So some lessons I've learned in doing these experiments at home. Here's an example of my first Parkhomov style test. It was a simple design, used a commercial off-the-shelf Watlow furnace. Just placed some thermocouples in there and fuel. The left side of the reactor had the fuel in it, right side was empty, and kind of compared the results of each side. Here's the results from that experiment. You can see here the magenta is the thermocouple measuring the furnace temperature. The red line is the thermocouple measuring the fueled side of the reactor. As the reactor heats up, the reactor side starts to get closer to the air temperature, until it reaches a point where the two cross and the reactor becomes hotter than the temperature in the furnace. And for about 12 hours, it stays hotter than the temperature of the furnace. And then the reaction starts to diminish, presumably. And then over time, the reaction quits, if there was a reaction. And then the whole thing fails. Both the furnace and the thermocouples all fail. So then the question I learned from this is, was there excess heat? And the fact is, I will never know. There were several mistakes I made on that experiment. And I appreciate those who helped me to discover these mistakes and improve. First of all, it was insufficiently calibrated. The test setup changed between runs, making pre-calibrations null. I was only using thermocouple measurements, and I found many times since that thermocouples, type K thermocouples, can oxidize and cause errors, especially the cheap thermocouples that you get off eBay. Those things can provide many erroneous results. And then the test wasn't repeatable because I destroyed the equipment in conducting the test, and so it was impossible to conduct a post-calibration. And also, it wasn't set up to be able to do repeatable testing. Things were not affixed properly so that you could have a repeatable test set up. So I learned from that, first of all, always calibrate with the current test setup. I've learned that time and again. Type K thermocouples, unreliable in my estimation. I've moved to type N thermocouples, and I would recommend those. Then I would definitely recommend at least 2 methods of measurement. I always use thermocouples, but I've now switched over to calorimetry, and I think that's, of course, the gold standard. You could do IR temperature measurement, but you're only measuring one spot typically, and so I definitely would encourage, this goes back to convincing yourself. Always try and have at least 2 methods of verifying your measurements. So I'd like to talk a little bit about some skills I've learned as a home inventor. And I think the most important of those is what I call repurposing. For those of you who remember the 80s and 90s American television series MacGyver, where you'd use common household items to make highly technical items, that's essentially what we want to get better at. And so I've provided some examples of that I've come up with. This was my idea for coming up with a glove box. I just took a regular everyday picnic cooler, put a Lexan lid on it, some plumbing fixtures attached, and it became my capable of argon purge glove box. Here's how I do my reactor sealing now. I've fought with swage lock fittings and continued to have to end up trying to grind down my alumina tubes to get those swage lock fittings to fit and get a good seal, and it can always prove difficult. Well, I've discovered now, you just use your hex reducing bushing from your hardware store, use some 2-part epoxy, and I found that this method of sealing a reactor loses almost no pressure, like I say here, over 200 hours at up 12 bar and above, with almost no loss of pressure. That's another easy method of just using everyday household items to run these experiments. For my fuel containers, Bob talked about how we've had problems with lithium getting everywhere. And especially when we started adding free lithium to the experiments, we very quickly discovered that it would destroy your alumina tube. And so what I came up with, and has proven very successful, is I just buy a thermocouple protection tube from Omega Engineering and get a stainless steel taper pin off of Amazon.com. And I found that you stick your fuel in that, and it's provided well over 200 hours of exposure to molten lithium without failure. And so that's another easy way to use everyday materials you can buy for those of us that don't have access to a machine shop, it provides an easy way to create a fuel container. Here's how I created my calorimeter. And for a first shot, it's worked pretty well. I just took your regular beverage dispenser, added a postage scale to measure water loss, and added a submersible water pump to add water once a certain amount of water had been boiled off. And so with that, I created a heat of vaporization calorimeter that can be left unattended for hours and sometimes days at a time, and it fills itself with water and then boils it off and fills itself again. And it's worked pretty well. There are some things that I'd like to improve about it. It's a bit, the time constants are quite slow, and it takes time for the thing to heat up and start boiling. So there's things I'd like to improve about it, but there's another easy way of using everyday materials to create the materials needed for these experiments. The other problem that we used to frequently have as experimenters is we are continually having our heating coils burn out. And so the way I've solved that, and I know other experimenters have done other things, is I just got a insulating fire brick and carved myself a insulating tube out of it. And then I use that to insulate the canthal. And what that does is it allows you to reach high temperatures with a smaller current load. And that has greatly increased the time of life of my furnaces. And so, for instance, this last one survived hundreds of hours at temperatures up to 1200 C. And it just recently died out on me, but it wasn't actually the furnace's fault. It was a faulty thermocouple that burned out and caused my my reactor to heat up too much. That finally was the end for this last furnace. But that's another way to get your furnace to last longer, is provide a little bit of insulation. And that has seemed to make it last much, much longer than an uninsulated coil of canthal wire. So some of my latest test results. Here's a couple of tests I've run recently. This first one was the first one I ran using the fuel formulation from the Rossi patent. This one I used Inco 255 nickel, and then I was able to obtain passivated lithium powder from Nanoshell. To prepare the fuel, I heated the nickel at 200 C for about 90 minutes. Mixed it in a mortar and pestle, and then added in the lithium powder, all in argon, and then heated it with a pure sine over 24 hours, up to about 1100 C. And unfortunately, no excess heat was seen with that experiment. Next, I tried using Hunter nickel, AH50. It has a particle size of about 3 to 6 micron. And again, the Nanoshell passivated lithium powder. For this experiment, I decided to try removing any oxide film on the nickel powder. And is that important or not? We don't know yet. So I heated it to about 600 C, and I mixed it with about 1% lithium aluminum hydride, so it would be in a hydrogen environment while I heated it to encourage microcracking in the nickel. And then I mixed it following that with a mortar and pestle with the lithium powder. And for this test, I tried using a triac chop sign instead of using the variac. And then also on this test, I tried using temperature cycling to encourage pressure cycling. And once again, unfortunately, over a period of about 1 week, with this temperature cycling, there was no evidence of excess heat. And I'll show some of the plots and results of these experiments. And then my last test that I completed just this week, I decided to try a larger fuel load on this one. And so I used some Chinese nickel off of eBay, just trying different things. and used a 5-gram fuel load and with 1 gram of lithium aluminum hydride. And I added a little bit of bulk, I should say lithium right there instead of nickel, and then tried that to see if a larger fuel load would result in being able to detect excess heat easier. And once again, unfortunately, no excess heat was observed in that test. So these are some plots from some of my recent tests. This is the one with the Hunter nickel, and this plot is with temperature. As you can see, I cycled the temperature, and this is over a period of days. And there's been some question as to whether temperature and pressure cycling might encourage the reaction. And unfortunately for this test, there was no excess heat observed. You can see this just zooms in on some of the temperature cycling. You can see the pressure cycling as well. And then I measure the COP based on how much energy I put into the calorimeter versus how much water is boiled off. And so you can see the water being boiled off, then filled up by the water pump, and then boiled off again. And from that, I'm able to ascertain a fairly accurate COP. There's calibration results. And so here's the results of the COP measurements. And so there's just my best estimate of, approximately where the COP curve goes. Now, you can see here that it looks like we're getting positive COP. It goes above 1. But what I've found, when we add the calibration in, is that the calibration actually went above 1 as well. Now, why is that? I think that's because the energy monitor I'm using is probably not as accurate with triac chopped power input. And so it underreports the input power. And so that's why we see the positive COP on these experiments. And so that again shows the importance of doing a proper calibration on each test setup. The data is kind of all over the place here, and that's just because as you run these tests, it kind of depends on where the temperature cycling is in the water fill in and emptying of the cycle as to what the measured COP is. But you get a pretty good idea from the many data points of where the real COP is. This is my latest test that I just ran this week. Now, the interesting thing on this test is just adding that little bit of bulk lithium results in the pressure. You can see over a period of several days, starting out at about 90 psi, had a data dropout here, but then by the end of the test, after several hours, I think it was actually over a day at 1100 C, we see the pressure dropping to a hard vacuum. Is that important? I don't know. Unfortunately, once again, I did not see excess heat on this test. So we're still learning what's important. But I think what we can see from these tests is, it goes back to the Edisonian, I did 10,000, where he did 10,000 tests, and he said, I only need to find one test that's successful. And, the 10,000 tests, we found things that don't work. And so as the home inventor, maybe that's our role, is where we help find things that don't work, and then occasionally we'll find things that do. And I think we can make a difference by just adding to the body of knowledge on things we observe in our testing. And eventually we'll find things that do work. So that's just the results of that latest test with the eBay nickel. And it looks like I forgot to put you can see the calibration here. The red is the fueled run, green calibration. And so the fueled run is right in line with the calibration run. So future plans for what I plan to work on in the future. There's been some question as to whether adding graphite to the mix might help out. Park Mob nickel had a large carbon content. I may try that. I think we need to experiment a lot with baking nickel, either in various atmospheres, different times. There's that key nickel preparation step that we don't understand yet to get the correct particle size and distribution and morphology. That's really where we could use help from the group in figuring that out. Then there's some other ideas of things that I plan to do in the future. Some needs to end up for the home scientist. The difficult thing for the home scientist really is to get the materials needed for these tests. And so we need access. We've been able to get access through Martin Fleischmann to a couple different nickel sources, but still we're limited to about 2 different nickel types. And so access to multiple nickel types. We still need a source for lithium powder. The nanoshell powder that I was able to obtain, it does not seem to absorb as much hydrogen as it should. I've noticed that the bulk lithium powder absorbs significantly more hydrogen than the nanoshell powder does. So we probably need access to another vendor for lithium powder, and that's proven very difficult, especially for the home inventor, to gain access to that. And then we need to start coming up with ideas of, either how we can use bulk nickel or bulk lithium, or other methods of fuel preparation, and ideas of how we can end up with the morphologies and things that are successful. And then really what I think would be very beneficial is if we were able to develop a low-cost calorimeter setup so that more people were doing calorimetry instead of just using thermocouples for measurement. Because as I've said, I really do not trust strict just thermocouple measurement. It would be nice if we had everybody working with calorimeters. And so coming up with a calorimeter design that can be made easily by amateurs would be a great thing, and it's something I hope to work on more in the future. And that's what I'd like to share today. And so thank you again for this opportunity.
And thank you, Brian.